2006 Form B FRQs. It was question number 4. So if you want more detail about how this was scored, you can go to AP Central to look that up. But I wanted it to examine exactly how you get a 4 on this question, because it's very vague. All it asks is this statistically significant? Do you have statistical evidence to support that this program does improve dexterity? So if I notice I have a before value and an after value, what I really need to know is how this sample of people increased or decreased after the program. So the first thing I do before I start this is I actually need to calculate the differences. And I'm actually going to do after and then subtract the before. I'm going to focus on positive values. If they improved their score, then they will have a positive value. So in my list one, I did 7.8 minus 6.7, and I pressed enter. And then I did that for every single value in this sample. And now I'm going to have that information in my calculator too. So if I'm writing a significance test, then the first thing I need to do is state, what am I looking at? What am I examining here? I'm examining the mean difference, the after score minus the before, in dexterity scores for the population enrolled in the program. My null hypothesis, remember, null means no change. So I'm saying there's going to be no difference between the start of the program and the end of the program. But the company's claim is that there is a difference and that the scores improve, which gives us positive values. Because I did after minus before, my claim is that the mean difference is actually going to be greater than 0 for this problem. The next thing we have to examine are our checks and assumptions. So first, independence. We are told the sample is random, and I'm going to assume that 12 is less than 10% of all the people enrolled in the program. Also, the one thing that's different for matched pairs, and that's what we're doing here, we're doing a matched pairs, we're pairing before scores with after scores, is you need to state how the data is paired. I actually kind of did that in the first part. I mentioned this, but data is paired by each subject, their after score minus the before. You need to add that in there. Then we have to assess normality. Well, this gets a little bit tricky because we're not told that the population is normal, and our sample size is too small to use the central limit theorem. Our sample is less than 30. So what we need to do is actually check for normality, and I'm going to go back to my calculator. If I go into my stat plot and I check the histogram, I'm going to zoom 9. Okay, I'm going to check to see how skewed this is. Now, we don't have a lot of data points, and I'm not loving the look of this histogram. I'm not getting that it's extremely normal, but I'm also not getting any heavy skewness, and I can't really tell outliers. So I'm going to go back, and I'm going to also check my box and whisker plots. Remember, I have to avoid extreme skewness and outliers. Oops, sorry, zoom 9. Okay. Once again, I see a long tail over here, short tail over here, but then I see a long part of the box here. I'm still not positive. The good thing is I don't see any outliers. I'm not exactly sure how to write this up. So the last thing I'm going to check, just to make sure I can assume that this is nearly normal, is the normality plot. Remember, with the normality plot, we're just seeing that the data is fairly linear, that there aren't any definite patterns. So overall, I mean, this data isn't perfectly linear here. I don't see a perfect symmetric unimodal peak in my histogram. But what we can say, and again, an FRQ is never going to not meet the checks and assumptions. So how I wrote that up is I said, well, however, normality is not unreasonable because the sample data does not show skewness or have outliers. No, it wasn't perfectly normal. It wasn't perfectly symmetric. It wasn't necessarily the center of the data. But it didn't have skewness or outliers, and that's really what you're for when you look at those three plots. I don't have to sketch the graph. I just have to mention that I assessed the normal, I assessed the sample data, and I didn't see any skewness, and I didn't have any outliers. So now that we've done all that, with conditions met, I will conduct a one-sample paired t-test at a 5% significance level. So let's move on to the calculations, okay, and what we need to show for the calculations. So first of all, your formula sheet, these are the two formulas it gives you. We have to adjust these formulas for our paired t-test. So how do we do that? So a couple things in our calculators. If I go back to my calculator and I do stat calc one variable stats, I can get my sample data. My mean differences, I'm going to call that D bar, 0.375, and my sample standard deviation is 0.367. So over here I'm going to write D bar equals 0.375, and my sample standard deviation is 0.367. Now I'm going to calculate my test statistic using the formula from your formula sheet. It says statistic. Well, that was our D hat, or D bar. So we have our T is going to be D bar minus the mean divided by our standard deviation of the statistic. Well, I don't have sigma, so I have to use the standard deviation from my sample, and then I divide by the square root of n. So T is going to equal 0.375 minus our mean claim, which was 0, divided by 0.367 all over the root of n, and our samples. When I calculate this test statistic, I end up with 3.54. So if I'm going to sketch that on my graph I have here, 3.54, that's pretty far out here. Okay. But I have to calculate the p-value so I can compare the p-value. Remember what the p-value is. It's the probability of getting this sample data, the probability of getting a sample of 0.375 if the mean is actually 0. So what's the probability that we get this test statistic? Well, we can use our calculator for this, and we're going to get the accurate p-value if we do that. And we can do inverse t. So if I go to vars, inverse t, the area, remember, it's always area, I'm sorry, not inverse t, my bad. We're going to do second vars TCDF. We have our test statistic. Our lower bound is going to be our test statistic. Look at how you shaded, 3.54. The upper bound is infinity. Our degrees of freedom, well, we haven't written that down yet. And make sure you do write that on your paper. 12 minus 1, which is 11. And I get a p-value equal to 0.002. So the area under that curve is 0.002, or 0.2%. So now we take that value and we are going to compare it to our alpha. Since the p-value of 0.2% is less than alpha at 5%, we reject the hypothesis that there is no difference. We have evidence to conclude that on average, subjects who completed the program increase their manual dexterity. Just another reminder of a way you could use your calculator to get a lot of this math, although to get a 4, you really want to do all of this work. You could go to, and if you scroll over to tests, remember the data is already calculator. I've put the data in the calculator. We're doing a t-test here. So if I put this data in, I set my null hypothesis to 0. My sample mean was 0.375. My sample standard deviation was 0.367. My sample size was 12. The only other thing I have to select is my alternate hypothesis. Well, remember what our alternate hypothesis was. We said that the mean difference is going to be greater than 0, that they're going to show improvement. And when I press calculate, I've given my test statistic, which we said was 3.54, and I'm given the p-value. So now I could check my calculations with the calculator t-test to secure that my conclusion is in fact true.